this one must be less than or equal to the yield stress. So what I'm saying here is that this one must be satisfied for your material to be safe. So that we did this one already. This one is also a criteria for yielding, meaning that once your stress, the von Mises stress reaches your yield strength, then you have your material to have yielded. This one, your material would have fractured. Okay? So because you have S1 to be greater than the ultimate strength, so that of course your material would have already separated. Next thing we have to consider is we have your fracture mechanics failure criteria. Again, that would be, so here as you can see, these are all, what I'm saying is that all of these are material properties. Meaning, when I say material properties, these are determined from test. So each material, aluminum, steel, alloys, whatsoever, will have their own ultimate strength and, of course, their yield strength. So these are material properties, and sigma 1 are the principal stresses, and your von Mises stress are the calculated values. So you compare calculated values with test values. That's when you know that your material will be safe or not. Another failure criteria that, well, it's trying now to, I mean, the fans of fracture mechanics now is growing, and for some reason a lot of industries now are adopting this failure criteria. So once you check your design, aside from doing all these steps, you also have to have a fracture mechanics failure criteria. So here you will be able to have your, what is this one? This is your stress intensity factor. So in fracture mechanics, this is the thing that you wanted to know. You already have this one here from that. So once you have this one, you always have that crack. So what's the assumption here? The assumption here is that your material will have a crack. Your material is not perfect, so it will contain a crack. So even if it contains a crack, there should be a certain length wherein that crack will not grow. I mean, yes, we allow the presence of crack because we know that our material is not perfect. But up to what size of crack do we want it to be? That's the A, half length of the crack. Right? So these are the things that you wanted to know. And how do we know, just like this one, how do we know that our material will be safe or our structure will be safe, given that we have A? So we have KIC, which is again a material property. So this stress intensity factor must be less than or equal to that fracture toughness. So again, this one is a material property, meaning that you can get this value from test. Every material will have this one here. So again, that's a material property, and this one is a calculated value. I think there's a chapter in the notes wherein you can read more on fracture mechanics. So at the moment we have now for theory of elasticity, we have 1 to 3 failure criteria. Actually, there's one more, which is the shear stress failure criteria, but we will be discussing that later. It's quite straightforward as well. Again, okay. So all of these, yes, we have this equation. So really, what's the assumption of mechanics or solid mechanics for this analysis? What's the assumption? You probably had your strength of materials or mechanics of materials in Polytechnic. So what's the assumption? Your material is? Okay. So for strength of material or mechanics of material, or for all of these theories to be applicable, your material must be what? Homogeneous and isotropic. Homogeneous meaning you have the same material the same material property in every location. Isotropic meaning the properties will be the same, or the modulus or the properties will be the same in all the direction. Homogeneous and isotropic. So, well, you can of course extend the use of this one for, say, composite materials. Alloys, it works. Composite materials, you have to adjust a bit, but for some reason it's being used for composite materials, which you will take next semester for your advanced materials technology. Okay? So what did I miss? So, when are you going to use this one here? For which type of material? Brittle material? Ductile material? This one is brittle material. For a ductile material, there is a more complicated equation for ductile material, which we won't go into. Okay? So those are the 3 things that you should remember. 1, 2, 3. Right. We have also discussed how to solve this one. From here to here, you have done that already. So I think when you did this one, you have already have to identify your invariants. So I think that's now straightforward because you've done something here already, and then you have calculated this one. So again, these things really are not a problem anymore. Just a few things to note before we move on. What about, we have discussed earlier, yes, so we have discussed earlier your hydrostatic stress. So this hydrostatic stress will be that normal stress, and that this will be all equal. So this hydrostatic stress will try to change the volume of your material. So we have a hydrostatic stress wherein this changes the volume of the material. So what about the stress that causes distortion or change the shape of our material? We have that deviatory stress. So how do we obtain this one? Again, this one is straightforward, wherein you have now your Sij. This one is, what did we have with this one? This one is your sigma ij minus, if we're looking at 3D, we're looking at 1/3 sigma kk, and then you have this bunker delta. Yes? So meaning this value is only present when I equal to j, meaning that you have this one to be 1, 1, 2, 2, 3, 3. Then you only subtract this one if you have your normal stresses. Let's try to make a, let's try to understand this one further. Sigma kk is actually your hydrostatic stress. So this hydrostatic stress sigma kk, what do I mean by this one? That is 1/3, sorry. 1/3. Okay, for 3D, we're still talking about 3D. Sigma kk, meaning you have a dummy index here, repeated. So that is 1/3, sigma 1, 1. So you have a dummy index here, repeated index, meaning there is a summation, repeated index. So you have sigma 1, 1, sigma 2, 2, sigma 3, 3. Yes? And so, if we're going to write your deviatoric stress tensor, how will that look like? So this one here, we have Sij, your deviatoric stress tensor. Let's try to write them again. That will be sigma 1, 1. So again, we have a symmetric condition. So this one is that. What about this one here? Okay. Oh, sorry, sigma kk. So sorry, this one is your sigma h. Let me remove that. Happened here. So let me change this one, sorry, just not to be confused. Right? Let me remove that. Okay? So sigma kk is sigma 1, 1, sigma 2, 2, sigma 3, 3. So once you have this one here, your sigma h is equal to 1/3 of sigma kk. 3D. What if you have 2D? So you have this one to be half of that sigma kk. So let's try to put in this value here. Sigma kk, right? That's what it says. And then delta ij. What's your delta ij? Delta 1, 1. And then we have sigma kk, delta 1, 2, sigma kk, delta 1, 3. I'm just trying to write now these values, delta 2, 1, sigma kk, delta 2, 2, sigma kk, delta 2, 3, sigma kk, delta 3, 1, and so on. Delta 3, 2. Right. So what can you deduce from this one? These values are zeros because delta, so if you can recall, delta ij is equal to 1 if I equal to j. This is equal to 0 if I not equal to j. So that this one will be 0, 0, that is 1, that is 1. There you go. So again, 1/3 sigma kk is simply sigma h. Let me write it here. Sigma, or sorry, Sij, small letter. So this one is a small ij. This one will be sigma 1 minus sigma kk 1/3 is actually your sigma h. Sigma 12, sigma 13, sigma 22 minus sigma h. Then of course you have a symmetric matrix. Okay, so what does this deviatory stress tensor mean? That will be that stress tensor that's going to cause distortion on your material. So we already removed that element that's going to cause changes in the volume. So if you remove this one from your stress component, so this is your original stress component, you remove this one here, which causes changes in the volume, then you have an expression which changes the shape of your material. So take note, it's just knowing, it's not just looking at the equation, it's really trying to understand what this equation means. So, end of your solution, you will be able to explain what's going on. Okay. Change in volume, change in shape. Change of the volume and shape, of course, you go back to your original stress tensor. Yes? Question? So, this has to change the volume, sorry. And this one changes the shape. Distortion. Geometry, shape. Deviatory stress. Yes, so we have now, we're quite stressed now, so because we have a lot of stress terms that we have to consider. Yes. Okay, so how do we apply that to the theory of plasticity? Let me check if I forgot something before we move on. Alright, okay, got everything. Any questions with the stresses? I want all of these stresses to be clear. The reason is that when we proceed, then we won't be reviewing the different stresses anymore, because next week I would like to start with finite elements. The ones you have in your notes is 2D, but I want it to be clear, so I probably will be starting a fast track with the one-dimensional finite element first. More like a review with your mechanics 3, but more additional theory. Heavier load rather than your mechanics 3.